A controller dealing with the failure of a quadrotor's motor is presented. Supposing that the fault has been already detected by the system, the approach here proposed considers to turn off also the propeller aligned on the same quadrotor axis of the broken motor. In this way, the resulting configuration is a birotor with fixed propellers. The control is designed by employing a PID-based controller, allowing to reach any position in the Cartesian space, dropping the possibility to control the yaw angle. In this case study, a straight-line emergency landing trajectory is planned. The birotor has to reach the origin of the Cartesian system in 20 seconds. The birotor stays for other 30 seconds in a steady-state condition. The tracking is quite accurate. The visible small oscillations are due to the continuous spinning of the birotor around its vertical axis. It could be seen that also the value of the uncontrolled roll angle remains very small. In order to better emulate practical issues, the same planned trajectory as before is employed, but noise has been added to the measurements signals of position, linear and angular velocities, and orientation. Moreover, initial roll and pitch angles have been set to 4 degrees to simulate the case in which the tolerant control is switched on and the initial conditions of both angles are reasonably non-zero. It could be noticed how the noise affects all the time plots. The stability is still preserved. The uncontrolled variables, like the roll angle, remain bounded as well as the pitch and position errors. In this case study, the presence of an obstacle has been simulated. Therefore, the planned trajectory is first a semicircle, with the duration of 20 seconds, and then a vertical straight line towards the origin of the Cartesian system. The duration of this part is of 25 seconds. The birotor stays in a steady-state condition for other 15 seconds. The tracking is again quite accurate. In the vertical part of the path, the desired pitch angle is 0 and the related error appears to be 0 as well. A spiral is here performed to show that in principle any path can be planned for the birotor. The price to pay is the impossibility to control the yaw angle. PID-based controller has been used to control both the translational and angular part. The stability proof exploits a Lyapunov-based method for perturbed system. It is in fact possible to verify that the pitch tracking error affects the performance regarding translational tracking. The tracking is accurate even with such type of trajectory. This proves the good performance of the proposed architecture. The uncontrolled roll angle remains bounded. The values of the propeller speeds do not saturate. The simulations here presented have been realized with the MATLAB Simulink environment.